So let's have a look at the four main standards which make up most of the traffic that we see on a network. And these are Ethernet, IP, TCP and UDP. As I've seen before, what we normally do is we normally split up our transmissions into different layers. So when we start up, we have some data, and we'll find out later that this data is a chunk of all the data that we're going to send. We then go through each of the layers, and each of the layers adds their own little bit of information to it to allow the data to be sent from one computer to another. At the lowest layer we have layer 1, or the physical layer, and that looks at the copper, fibre, the cables, the electrical signals and so on. Above that we have the layer called the layer 2 layer, or the data link layer, and it's up to the data link layer to be able to make sure that the data gets from one place to the next. So as we go through a network, we might change onto different media, different networking types and so on. It's up to the data link layer to be able to make that happen across each of the networks which we span. The layer above is known as the network layer, or layer 3, and at this layer we get the concept of a network address. Above that we get the transport layer, and it's up to the transport layer to be able to segment our data into chunks and then send each of these over the network and then to be reassembled at the other end. Above that we have the application layer, and it's up to the application layer to create a session between the two machines and to be able to translate the data through a sequence of messages. So the way that we abstract the network is in these different layers. At layer 2 we often define that in terms of a data frame. So in an Ethernet network we transmit data frames over the network. At the IP or network layer we define them as a data packet, so a data packet translates over the internet or the network. And at the transport layer we define these as data segments because they're really chunks of our data. And then at the layer above that we define application layer messages. So each layer adds their own little bit. Normally we add a header. So the TCP layer adds this bit here, the network layer adds this bit here, and only really at the data link layer do we frame it by adding a start and an end. So this really defines the start and the end of our message. So let's look at the three standards that really make up much of the communications on the internet. That's Ethernet, IP and TCP. We'll also look at UDP, which is used less often, but most of the communications that we see are really based on these three standards. The way we normally view network traffic is in terms of a layered model, and this allows us to be able to keep compatibility between different types of systems and then to be able to plug in different types of protocols. At layer 1, or the physical layer, we get the cables, the electrical signals and so on to define a standard. Then at layer 2 we have the data link layer, which is responsible for really getting the data from one node to the next. As we go through an internet connection, we might change different types of networking. So it's up to the data link layer to be able to get it from that one point to the next as it hops through these interconnected devices. And the most popular type of data link layer is Ethernet here. At layer 3 we get the concept of a network address. It's up to the network address to be able to define a destination node so that the intermediate nodes can actually route the data between them and for it to get to the destination. Above that we have the transport layer, which is responsible for taking large amounts of data and then segmenting it up into segments and then marking each of these segments so that if they arrive at the other end of the sequence or there's any missing, it's up to the transport layer to request a retransmission of the data. And the most popular here is TCP and UDP. Above that we get an application layer, which is really responsible for the messages that are used to be able to transmit the data from to and from our application. We might use HTTP for web, FTP for file transfer, Telnet for remote connections, and SMTP for sending email. Normally what happens is that we take our chunk of data or our segment. We might have a whole lot of data that we're sending, but we can't just send it all onto the network, so we segment it up into smaller segments. To give you an example, this is about 1500 bytes for Ethernet. That's the maximum that an Ethernet packet can actually hold. So each layer adds their own little header onto the data, and each device will look at this header, or each layer will only look at its own header part. So the transport layer adds a header here, network layers adds a header, and only at the data link layer do we actually frame the data by giving it a stop and an end. So this is what's transmitted over the network. When we look at Ethernet, Ethernet is fairly well standardized. We have preamble, ones and zeros that starts the Ethernet frame. Then we see a destination MAC address, which is 6 bytes long, and a source MAC address. So this defines the hardware address of the machine who's sending and the hardware address of the machine who's to receive the data. Then Ethernet can encapsulate many types of layer 3 data packets. So here we actually define that it's either IP or app and so on. Then we would embed in our IP packet with a checksum at the end, very basic checksum, just to check if there's any errors on the Ethernet frame. We'll go into more detail about IP and TCP in a little minute. Normally what we would do is to view our data is to use something like Wireshark. So this shows an example of a captured traffic here. And we can see here that this contains the source address, the destination address, and the source address, and there's the IP type there. Okay, so for each of these, each will have an Ethernet frame. You can see the protocol is the high level protocol which is contained in them. So let's have a look at our initial data. So we'll just have a look at a simple web page example. Okay, so in Wireshark we can actually see our different layers here. So there's our layer 2, layer 3, layer 4. Sometimes we get even higher level layer. So there is our layer 5 to layer 7 for HTTP. Okay, but for this one here, let's have a look at the Ethernet details. So you can see there's the destination MAC address. There's the source MAC address, and here is the IP part. The first 3 bytes identify the hardware manufacturer, so in this case 005056 represents VMware. And we should be able to see the MAC addresses changing as we capture the packets. This one here is a special MAC address. This is a broadcast address which is sent to all the nodes on the network. And as we go through it, we can see different MAC addresses being identified. Okay, so we'll come back to what the ARP packet actually is later in the presentation. Okay, so each of the packets here that have been captured are encapsulated within inside an Ethernet frame. So let's now look at the Internet Protocol, focusing on IPv4, which is one of the most successful networking standards which has ever been created. In fact, it's so successful that it's outgrown its potential, and we have run out of network addresses and have moved towards IPv6. But most of the traffic that's on the internet just now is still IPv4. And with IP, we can either set up public addresses, which can be routed across the internet with a capital I, or we can have private internets with private addresses. Then we can use devices such as network address translation or proxies to be able to route the data in between. And with IPv4 we have a 32-bit address, and with 32 bits address we split it up into bytes or octets and then put a dot in between. Then we can classify them in their basic scope of the network by defining 5 different classifications of addresses. And the classifications differ in where the network part actually is. For Class A, the network part is this part here, or the first octet. And devices that are routing will only look at this part and will ignore this part. So an address which starts with a 0 is a Class A address. And then the next bits define the network address that's been allocated. So in this case we can have all zeros to all ones here, which gives us from 0 to 127. And because all zeros is reserved for the network and all ones is reserved for a broadcast address, we normally can only allocate up to 126 addresses. The next part here is allocated to the hosts, number of hosts that we have on each of the networks. To be able to differentiate and to tell a machine what is the network part and what's the host part, we use what's called a subnet mask. And in this case, 255, or all ones, defines that this is the network part, and all zeros here defines that this is the host part. So you can see here that we have 16 bits for the network part, so this defines the subnet mask, and here we have the host part, which defines zeros. Class B begins with a 1 and a 0, so the range that we can get goes from all zeros here, 128, to 191, or all ones here. This gives us 65,384 different types of networks, different network addresses, and then we can have on each of these networks 65,534 hosts. Class C provides the smallest number of hosts, and it starts with 110, and that gives us a range from 192 right up to 223. We can get lots of networks allocated here, but only with a few hosts on each network. Then we can have a Class D address, which is multicast, and with multicast we can have one address. And then we can have multiple subscribers to that one address, and that's defined as multicast. So we can send it to one address, and then many machines can actually receive the data by subscribing to that one address, and that is defined in Class D, which are the multicast addresses. Then we have Class E, which are for research. Okay, so these are important classifications here, A, B, and C, and those are our main address pools that are allocated addresses. The IP header looks like this. The first 4 bits defines the version number, and this can either be version 4 or version 6. In this case we see this is IPv4, but it could be IPv6. Then we've got a header length type of service, which hopefully we'll have time to look at later. Total length, an identification field, fragment offset, and this is an important part here, the time to live field. So you can see in this case our time to live field is 128, and really what that is that each intermediate device or each router will decrement that TTL value. So we might start off with 128, but each device will decrement it by a certain amount, and we don't want data packets to transverse the internet forever. So whenever that value becomes 0, the data packet is deleted from the internet. After that we get what's called the protocol field, and the protocol field defines really what's coming next. So in this case a value of 6 defines that what's coming next is TCP. Then we get this a basic checksum. Then after that we get the source and the destination IP address. So let's have a look at our capture here. Okay, IPv4, there's the header. Got some flags here. There's the TTL field, 128, and there's TCP. So that value of 6 defines that we have TCP as the next part. We have a checksum, and then we have our source IP address. This is the machine that's sending, and then destination IP address. Then after that we have our TCP part. Let's have a look at the genius that is TCP. Okay, so for recap, there's Ethernet, there's the IP header. Key things with IP header: source IP address, destination IP address, TTL field, protocol, version number. As we remember, the protocol field, if it's a 6, then it's TCP, 1 is ICMP, 17 is UDP. So if the value is 6 there, then what we have coming next is the TCP header. And the TCP header has the concept of a 16-bit, this is 16 bits across here, 16-bit TCP source port and destination port. And it's these two things, along with the IP addresses, which makes that connection unique across the whole of the internet. So no other connection at that given time has the same IP addresses and the same source and destination ports inside the internet. Then we have a sequence number for the data that we're sending, and an acknowledgement number which can acknowledge data that's been sent to us. After that, the important field here is the flags, and we'll have a look at how these flags are actually used in a little minute. But it's really TCP that provides the reliability and the robustness that we see on the internet. And the key to this robustness is inside the flags. So there is a flag called a SYN flag, and the SYN flag is sent at the start of a connection between a client and a server. So the client wants to make a connection. it sends a SYN flag. If the server accepts the connection, it sends a SYN and an ACK flag back. And then if the host wants to complete the connection, it sends back an ACK. And this is defined as what's called a three-way handshake. Once this communication is over, then we have now a connection made between the client and the server, and data can then get transmitted. We have a sequence number for our data, so that each data packet that's actually sent actually has a sequence number, and then we can actually acknowledge that we've received all the data by sending back an acknowledgement. The 21 here defines that, in this case, the server expects to see back packet segment number 21. And it's these three handshakes that allow a connection to be created. So if we take an example here, so we can see here, this is an example where we have SYN, a SYN-ACK, and then an ACK at the end. The two important pieces of information here that's actually created is what's called a source port and a destination port. In this case, we are using this port to define our TCP port, and the server is using this port to connect. When the communication comes back, the server uses its port to communicate back with the port that we've actually created. So let's have a look at that in Wireshark. Okay, so there is our SYN, our SYN-ACK. Here is SYN-ACK. And there is SYN. And then at the end we get ACK. The key thing here are the actual ports that we've created. In this case, 2427 is our source port, and 80 is the destination port. So 2427 is unique for this connection, and it connects to port 80 on the other side. SYN provides us with the start of a communication. So if we want to see the whole communication, we can then just follow the stream, and this shows us all the data that was associated with that connection. The SYN is an important data segment flag because it defines the start of the connection. Okay, so there shows an example. It's connected to a server. SYN, SYN-ACK, ACK is their three-way handshake. Okay, so here we go. This is SYN. This is our port. In this case, Wireshark is replacing it with a name or that it thinks the protocol is, but it's just a number really. That's the destination. The server responds back with a SYN-ACK, and then we respond back with an ACK. The other key things here are sequence number and the acknowledgement number. Remember, the acknowledgement is that the machine is expecting to see this data segment next. There are other things such as the window. The window defines the maximum number of data segments that can be sent before the other side has to stop and wait. There are certain standard ports which are used on the internet that when we connect to a server. 21 is FTP, 22 SSH, that's a remote telnet with security. Then we have Telnet 23. SMTP is email sending. Port 25. DNS is domain service. HTTP is web. POP3 is reading email, 110, and so on. So for the service that we're interested in, we would actually look at the port, and that's the port we would normally connect to. Obviously, if an organization wants to block something, what they do is they will block the SYN coming in on a certain port. So if we want to block incoming FTP, we might block port 21 for an incoming SYN so that the connection can't actually be made. So we'll have a look at this, and what we should see is we have port 80 for HTTP, and when we look at other traffic we should be able to see that we have different ports actually used. Okay, so this is a unique connection. If we bind the IP address of the client, IP address of the server, TCP port of the client and TCP port of the server, then we have a unique connection across the whole of the internet. Unfortunately, some of the protocols, as we'll see, have got some weaknesses, such as FTP having plain text, Telnet also, so that any information sent with FTP and SMTP, DNS and HTTP are open to attacks because they're sent in plain text. So the last little protocol that we'll look at in this section is UDP. UDP is much simpler than TCP and doesn't actually require a three-way handshake. Basically, data is just sent from one machine to another and no acknowledgements are created at all, and there's no handshaking of the data. So it's seen to be unreliable, and it's often used in protocols where a high-level protocol is used to build in that robustness. It's fairly simple. It's just a source port and destination port, as we've seen before, basic length and a checksum, and that's it. So then we have a UDP port and a server port, UDP server port, and the data is really just sent. So you can see here there's the source port, and we have a destination port of 53 in this case. Many protocols use TCP. One protocol which uses UDP is DNS, and that's on port 53. So these are some of the other ones. SNMP is used to be able to interrogate devices. It uses 161, UDP 161 and UDP 162. So let's have a look at that. So as I said, DNS uses UDP, so we'll have a look at that one with Wireshark. Okay, so no three-way handshake here. Just go straight away, and we can see the port we're using in this case, 632226, destination port 53. The DNS server replies back on port 53 and then uses our destination port, and some more communication between them back and forward. Okay, so UDP is a very simple method of sending data. Not as complicated as TCP, but is seen to be connectionless and faster than TCP. Okay, so that's provided an overview of 4 of the most important standards in the lower layers of networking: Ethernet, IP, UDP and TCP.